Hi there, and welcome to 7th grade math, looking at Unit 1, Lesson 4. Today's lesson is on scaled relationships. And so we're going to continue our study looking at various shapes and comparing their lengths and their angles to see if these are scaled copies of one another. And so we began off today's lesson looking at 3 different quadrilaterals, and it said each of these polygons is a scaled copy of the others. And what it wanted you to do, if you recall from your lesson, was to kind of decide if that was true or not. And so it began by first taking a look at naming 2 pairs of corresponding angles and deciding what you can say about those angles. So for example, angle A corresponds to angle E, which also corresponds to angle I right there. And you might have done some different things to say, well, how do I know if those are corresponding? How can I be sure? And you can do it a couple different ways. You could have decided, let me use my patty paper and let me get a new piece that's a little bit used. Let me use my patty paper and I can maybe make a copy of that angle, and then I could use that copy to then confirm whether it is the same. And so you could look there, it's the same angle, and that's one way to see if that is going to be a corresponding angle there. And you could do that with all 4 of them. You also perhaps took out a protractor today, and by doing so you place, and to do this I'd like to maybe highlight this a little bit for you so it stands out. So you could take a line and a line, we'll take those there, and then you could put your protractor on top of that to see what might that angle measurement be. And when we look here, we put our point there and we go to the 0, so we're looking at the inside measurement here. And when I look at this line, it ends up somewhere between 50 and 60, so we probably estimate that's probably about 55 degrees for that angle measurement. If I did that same thing over here on this shape, and here's E and H, just kind of color that so it's a little bit brighter to see, and then pop this in right there, we see that once again, yep, it's still going to be coming up right there to about the 55 degree mark. So we can notice using a protractor as well as the patty paper that these shapes do indeed are a scale relationship. There's a scale relationship there between the angles, and we didn't look at the lengths, but the angles at least correspond and we're in good shape. When you went to the second page, or next page, we were looking at a similar set of shapes, and they said once again that these are a scaled copy of the others, and we'd already checked the corresponding angles. Then we moved to start looking at the distances. But if you notice, what we're looking at today that says, well, because these lines are on diagonals, it's hard to tell how long they actually are. I could maybe use a ruler to figure that out, but in this case, I wanted to use the lines across. So looking at a line like DB, I notice it goes 1, 2, 3, 4 lengths across, and then AC up here was 6. We went 1, 2, 3, 4, 5, 6. And then we had to line up and decide if that's the case, then what about these other pieces? What about HF and LJ? And you found out that things like HF right here was 1, 2, 3, 4, 5, 6. So it's 6 across right there. And LJ, the little one, LJ, was equal to 2. And then similarly, you found out that, LJ right here is equal to 2. And then over here, when we did the vertical part, AC, A to C, you went to E to G, so we do EG. And for EG, we find out that it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then here to go I to K, 1, 2, 3, I and K is equal to 3. And at that point, we look at the values and we notice that they seem to be related. For example, to go from a 4 to a 2 is a scale factor of 2, just like over here, or half, sorry, is times a half. And 6 to 3 is also times a half. So our scale factor between these 2 triangles is 1/2. But when we look at 4 to 6, we see that it's growing, right? It's larger there. I'm going from a 4 to a 6, or I'm going from a 6 to a 9. It is increasing. Now it's increasing by how much? Well, to do that, I'm looking at if I go from a 4, or if I look this way, if I go from the scale factor one, what I'm looking at, the 6, so scale factor, and I divide that by my original, that's how I can find out what my scale factor actually is. So my new shape, or my new maybe I say my new one. So my new shape divided by original shape is going to be my scale factor. So in this case, my new shape was 6, and my original was 4. So my scale factor is reduced 3 over 2. All right, and that's what we're looking at there. So go here to here is 3 over 2. Different ways of deciding what is happening between the scaled copies of these shapes. Okay, so using that same idea here, we have this shape where there's a larger figure, it's a scaled copy of a smaller figure. And what I just said a second ago is that the new shape divided by the original shape is going to tell us what our scale factor is going to be. And so the question began today with if AE is 4, so from here to here, if this is 4, how long is the corresponding distance in the second figure? So I wanted to find out what this is going to be. Now I can do that because they gave me the value here of this length being 6 and this length being 15. Now that's enough information for me to notice that the new one, 15, divided by the original 6, lets me know there's a scale factor there. 3 goes into 15 5 times, and 3 goes into 6 2 times. So my scale factor is actually 5 over 2, which means I'm multiplying, so I'll write this in, scale factor equals 5 over 2. So that means to go from 6 to 15, I multiplied by 5 over 2. So, in solving this question here, what about the length of 4? I take 4 and I multiply it by 5 over 2, and 4 becomes 4 over 1. 4 times 5 is 20, over 1 times 2 is 2, and 20 divided by 2 is 10. When you looked at IK, it said, well, IK right here, this distance from I to K happens to be 5. Now, if that's 5, I know that I'm going to have to find out, for in this case, wants to know what is BD. Well, BD is my original, so I know I have some number. And if I multiply it by the same scale factor, 5 over 2, I end up with, let's say, 5. So that's how we're setting up the second question here. We're looking at a scale factor of 5 over 2 gives me the solution of 5 here. So I'm going to work backwards. So to solve this one here, I know I'm going back the other way. 5 over 2 is also, it could be like 2.5. You could think of it that way. So I have a number times 2.5 equals 5. And in this case, what I could do is I could divide both sides by 2.5, or I could do some fraction work here, and I end up with what I'm missing here. In this case, BD is equal to 2. Another way you might have decided to determine to solve that is you could have multiplied by the reciprocal. You could have said that BD times 5 over 2 equals 5, and then multiplied both sides by 2 over 5, and then 2 over 5, and that would cancel out. This would cancel 2, 2, 5, 5, and then BD would be equal to 5 cancel out, just the 2. So different ways of looking at that there. Again, that's what you did in classes, just kind of review. So then we looked at two quadrilaterals, and you had to decide if those were scaled drawings or not, and you probably analyze what was going on there to see what's happening with the parts. And again, that was a part that you did in class. You also then took a look at those same things to decide on the distances. Were they the same? Were they not? Did they measure up the right way? You know, the XY distance happened to be 6, the JN was 9, and the ZC was 4, and the SH was 6 when you looked at those things there. So the scale factor may not quite have worked the same way as it did before, but the key thing here was looking at the measurement of the angles. The angles just didn't quite work out when you looked at this one. So after going through all that, we went, it's just not going to quite work out. But let's take a look at the last one here from the 4 in class. It had two quadrilaterals like this, where you notice your angles were all the same. That was pretty good, 120, 120, 120. So the angles matched, but when you looked at the lines, to go from a 2 to a 1, the scale factor there looks like we are multiplying by a half, right? Where we're cutting in half. So I would expect that if I had a 4, I should cut that in half, but half of 4 is 2, not 3. So while the angles are correct, we notice that the side length, corresponding side lengths, also need to have the same scale factor. In this case, they did not. All right, so let's take a look at kind of our lesson summary. What we're looking at today in this lesson was that we're looking at scaled copies, and that all distances in the copy can be found by multiplying corresponding distances in the original figure by the same scale factor, whether the endpoints are connected by a segment. That means it used to be we would say this was 2, so because that's 2, I can look here and say 1, 2, 3, 4, 5, 6. So if that's 2 and that's 6, my scale factor is times 3. That's true. But we could also, what this is telling us today, is we could look here and say, well, I could look also at B to F, and if I know that B to F is 2, then I can also look at this corresponding part, even though they're not connected initially, and say 1, 2, 3, 4, 5, 6, that's 6, and I can see the same scale factor of times 3. The other part here is that all angles in the copy have the same measure as the corresponding angle. So this 42 matches this 42, and this 60 matches that 60, and 78, that's 78 there. So that helps us understand why a shape might be a scaled copy and why it may not be a scaled copy. While I could take a shape like this and say they all have 90-degree angles, that's great, but to go from a 2 to a 1 is a scale factor of multiplying by a half, but half of 3 is not 2, so this would not be a scaled factor there. Let's take a look then at today's actual homework, looking at lesson 4 for unit 1. It begins by asking you to decide all the statements that must be true for any scaled copy of Q of polygon P. So the side lengths are all whole numbers. Do all these have to be a whole number? No, they don't have to be whole numbers. They could be fractions, they could be decimals. The side lengths can be anything as long as they correspond to one another. They're a scaled copy. So we would say no to that one. The angle measures are all whole numbers. Well, I began with 125, 35, 250, 80, 135, and 90. Are those all whole numbers? Yes. So since they already are whole numbers, then we would say then they have to remain whole numbers. They can't change. That's a yes for sure. It says Q has exactly one right angle. Well, in my original, I have one right angle, which means my copy needs to have one right angle. I can't change the angles around. It needs to be exact. D, if the scale factor between P and Q is 1/5, then each side length of P is multiplied by 1/5 to get the corresponding side length of Q. And again, this is about scale factor, so we would say, yeah, as long as I multiply by the same thing for each side length, then that is going to be absolutely true all the time. That's the only way to get a scaled copy. For E, if the scale factor is 2, each angle in P is multiplied by 2 to get the corresponding angle. Well, from what we recall, the angles have to stay the same. We already said the angles has one right angle. We have angles are whole numbers. Angles have to stay the same. We cannot change our angles ever, or it won't be a scaled copy. So we're going to say no to that one. And it says Q has 2 acute and 3 obtuse. Acute means, remember, we have a 90-degree angle, so that's our 90. So acute is going to be less than 90, and an obtuse is going to be greater than 90. So when we look at our acute, back in our picture here, this one is acute, and this one is acute because they're less than 90. And then I have a 135, a 250, and 125. Those are obtuse. So I have 3 obtuse, 2 acute. So we would agree with that statement and say, yes, that is going to be true. Because again, the angles will stay the same. Let's look at number 2. Number 2, it shows us a picture of a quadrilateral. It says here's quadrilateral ABCD. Quadrilateral PQRS is a scaled copy of quadrilateral ABCD. Point P corresponds to A, Q to B, R to C, and so on. So what it's kind of giving us an idea is this. It's like you're going to draw another one. It doesn't have to be exact, so it's just a little sketch here. Let's say I drew another quadrilateral, And it said that P goes to A, so there's P. It said that Q goes to B, we'll call that Q. C goes to R, there's R, and S goes to D. All right. Now, if the distance from P to R, so here to here, if this distance is 3 units, what is the distance from Q to S? So it wants to know what is this distance right there. That's the part I'm trying to figure out. So to find that out, we have to look at our original shape. Our original had a distance of 1, 2, 3, 4, 5, 6 from A to C. So if 6 across from A to C is true and P to R is 3, I need to determine my scale factor. All right. Again, the scale factor is going to be our new shape, right? Our new divided by the original. And if that's the way that works out, our new one is 3 and our original is 6. So our scale factor is a half, or multiplying by a half is our scale factor. Knowing that, now I can take a look at this other piece, BD, to decide what's happening between B and D. And so in this case, B and D is 1, 2, 3, 4, 5, 6. It's also 6, which tells me that my distance from QS will be 6 times the scale factor times a half, and it will also equal 3. So that's going to be the length from B to D using the scale factor of a half. Let's take a look at the next one here. In the next problem, it says that figure 2 is a scaled copy of figure 1. And it wants you to identify the points, back out a little bit there, identify the points that correspond to A and C and label them P and R. So A is the tip, so we'll call this one P. C is kind of in the little inside there, and so we'll call that R, and that's the first part. Then it wants to know what is the distance between P and R. Well, distance between P and R is 1, 2, 3, 4, 5, 6. Looks like 6 to me. That's what I would say. So we would say 6, and you might say 6 units. For B, identify the points in figure 1 that correspond to points Q and S. So if this is Q and this is S, it says label them B and D. So we would go ahead and label this B to match with Q and D to match with S. It then asks the distance between B and D. Well, the distance between B and D is 1, 2, 3, or 3 units. Okay, so this is kind of nice because now we have some nice straight line units here of measurement. We can say that that's 3. We know that this one right here is 6. And we use that information, we can find out some other things. Well, good thing, they want to know the scale factor. What's the scale factor from figure 1 to figure 2? Well, let's look at some corresponding parts. Even though they don't touch each other, we can then look at if B to D is going to be 3, I could look at these ones and say, well, if that's 3, then what's this? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know that from B to D, in the new B to D over the, sorry, backed up here. The new one, if the new one's QS and the original is B to D, and this one happens to be, what do we say, 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. And the original was 3. Then our scale factor is 9 divided by 3, which is 3. I could check that out a couple other ways. I could take a look at the easy one here and say, well, this is 1, 2. So same idea for for the new PR, divided by AC, the original. I have 6 divided by 2, which is still 3. So my scale factor is going to be multiplying by 3. And it says GH, finally, are 2 points on figure 1, but they are not shown. So they're not there. We don't know what they are. The distance between G and H is 1. Okay, again, this is figure 1. GH, it has a length of 1. What's the difference between the corresponding points in figure 2? Well, to go from figure 1 to figure 2, I multiply by the scale factor of 3. And in this case, because if my original is 1, I'm going to do 1 times 3. We can call this figure 2 so you don't get confused with numbers here. Figure 1 to figure 2 is times 3. So 1 times 3 is 3, and so our solution would be 3. Let's look at one final one, which is actually a review from, it says grade 7, unit 2, lesson 4. So we'll come back up to it later on, it looks like. It says to make one batch of lavender paint, a ratio cups of pink paint to cups of blue paint is 6 to 5. So my pink to my blue ratio is 6 pink to 5. Find 2 more ratio cups of pink paint to cups of blue paint that are equivalent to this ratio. Equivalent means that they're going to be equal to each other. So to do that, what I'm going to do is I'm going to multiply everything by a scale factor again. So I can go ahead and, for example, multiply everything by 2 over 2, because it's really by 1, right? 2 over 2 is 1, and that could give me something like 12 over 10. That could be an equivalent ratio there. I could also take 6 to 5 and maybe multiply it by, I don't know, let's multiply by 5 just for fun. Why not? 5 over 5 is just 1, so I'm not changing anything. 6 times 5 is 30, and 5 times 5 is 25. These would all be equivalent ratios, and those work out just fine. A variety of options for you there. You can pick whatever numbers you want to multiply by, as long as this is your, we just kind of say over here, that's your big 1. Nothing is going to really change. Hope that helps you out today, and you have a great day.